I'm an application engineer here on our manufacturing solution side. So obviously we are talking 3D scanning here today with the Creaform Cube R automated scanning solution, but I also deal in different other additive manufacturing technologies through Stratasys, through Desktop Metal, and a bunch of other hardware-based solutions that we can offer. So with that being said, let's get started on our topic today, which is our Creaform Cube R automated scanning solution. So we're going to take a brief overview of the Cube R system, see what kind of integrations it has, what the different capabilities are, what kind of specifications the system has, and see if it might be able to fit into an application that you have in mind. So just an overview of the Cube R. The recommended part size, we can do parts up to 3 meters in length. So length, width, height, 3 meters, as long as the part fits within that bounding box, the Cube R can safely process that. We have an accuracy of 30 microns or 1.2 thousandths of an inch, and a mesh resolution of 50 microns or 2 thousandths of an inch. And we'll go into a little bit more detail the differences between accuracy and resolution and what that actually means in terms of real-world application. The Cube R also has fully integrated safety systems to make sure that the system can't be run and will prevent any sort of employee injury while in operation. It also has an automatic calibration, which is really nice to prevent accuracy drift over time. So you can just program that in to the robot's running program, and it'll self-calibrate. The whole system is run off of a Creaform MetroScan system combined with a FANUC M20IA robotic arm and a high-capacity 360-degree turntable. So expanding on that robotic arm, it's a 6-axis arm combined with a 360-degree turntable for 7 total axes of motion control. The arm itself has 0.08 millimeters of repeatability, a max reach of about 1.8 millimeters, kind of ties into our max part size of 3 meters, and a 1,000 kilogram or 2,200 pound capacity automatic turntable. So if we do have parts that large, a really nice feature of the turntable is that it is forklift compatible. So can't see it in this, you can see the forklift fork slots here on this side, and you also have another set on the longer side as well. It's very nice to have that forklift capability when we're dealing with thousands and thousands of pounds of parts. And what you see on that table on the right there is just, if you're curious, the different max speeds in degrees per second of the joint. So J1 is joint 1, and that is the base of the robotic arm attached to the control cabinet, with joint 6 being the wrist attached to the scanner. So how does scanning actually work? It's a 2-part system. Like I mentioned, it's a robotic-mounted Creaform MetroScan. So the MetroScan operates with 2 main pieces of equipment here. We have the actual scanner, the laser scanner that's attached to the end of the robotic arm that you can see in the foreground here. It almost kind of looks like a disco ball. And then in the background, in the top corner of the scanning cell, we have the CTrack device. So this is the dual cameras that you see at the top left of the screen. And that camera system is going to be watching the cell and using different information gathered from these positioning targets. A little blurry in this photo, but you can see they are the white dots with the black rim that are both on the scanner itself, which is on the end of the robotic arm, as well as in the bottom right of your screen, you can see that those targets are actually attached to our turntable as well. And what this allows us to do is the CTrack is tracking these targets both on the part as well as on the robotic arm. It uses that information to create a reference frame. So when we're doing these 3D scans, we always need 2 pieces of information. The first piece, we need a reference frame. We need some way to find our way back home. We need to leave a trail of breadcrumbs, so to speak, so that we can chain all of our pieces of data together in an accurate and efficient manner. So if we didn't have a reference frame, we would just kind of be creating floating data in the middle of nowhere with no inspection application, so to speak. So the CTrack is really the key to the solution there in creating the reference frame. Once we have that reference frame established, now the laser scanner comes into play. So that the ball with the positioning targets on it that's the laser scanner, and that will begin to project, as you can see on screen, this crisscross laser array on the part surface. There's a camera system in the laser scanner itself that will watch those lasers and observe how they deform across the part surface, and then that will allow it to pick up the 3D surface deviation that we're looking for in our measurements. So the scanner itself picks up the 3D surface information, and the CTrack then uses the reference geometry, or the reference targets, to place that surface data gathered by the scanning system into our global orientation, so that we can then measure from the far end of the part to the far end of the part accurately. Getting specific on the actual MetraScan unit, you can see a nice rendered image there. So like I said before, accuracy down to 1.2 thousandths of an inch, resolution at 2 thousandths of an inch. And so what do these actually mean in terms of real-world application? Accuracy is going to be your point-to-surface accuracy. So if you have a cube that is exactly, the top surface of that cube is 5 inches off of your tabletop, and you scan that surface, that those points are going to be generated within an acceptable error cloud here, in this case, of 1.2 thousandths of an inch above and below 5 inches off of your tabletop, if that makes sense. So accuracy is your point-to-surface accuracy that the scanner can provide. Resolution is how densely packed on that top surface of our imaginary cube here are those measurement points. So very similar to HD TVs versus standard definition, the higher resolution you get, the more points you pack onto that surface per square inch, which means you get a crisper image of what you're trying to scan. So these accuracy and resolution are going to be the two main specifications that kind of guide you in a direction based on your application. They do generally trend together. As we need more accuracy, we generally need more resolution, but they're not joined at the hip. You can definitely have high accuracy scans at a low resolution or high resolution scans at a low accuracy. It all depends on exactly what kind of geometry you're trying to scan. So in terms of real world application, what do these two specifications tie into? Accuracy ties into your tolerance requirements. So if you have something that is plus or minus a half of an inch, can this scanner scan it? We can do plus or minus 1.2 thousandths of an inch. We definitely can scan it. It may be overkill, so that might be a conversation to have. If we're looking for something that's plus or minus 1/10 thou in terms of tolerance, where we're doing 1.2 thousandths of an inch, again, maybe that is out of our wheelhouse here with this scanning system. So accuracy ties into tolerance requirements. Resolution ties into your minimum feature size. So if you can imagine, if we're scanning at a 1 millimeter resolution and we want to take a measurement of a 0.5 millimeter hole, we can't actually fit. If we're only putting a point every 1 millimeter, we are going to just gloss over that 0.5 millimeter hole because it's actually smaller than our point resolution. If we wanted to scan a millimeter hole, we'd probably want to scan it around a 0.2, or excuse me, a 0.5 millimeter hole. We'd want to scan it about a 0.2 to 0.1 millimeter resolution so that we can fit enough points inside of that hole to get a good measurement. So we want to make sure that our resolution is appropriate for the smallest feature size that we're trying to measure on our scan. So that being said, if we're trying to measure like a large car body or something like that, where we're just measuring from a large surface to a large surface, we could maybe use a 5 millimeter, 10 millimeter, 20 millimeter resolution, which will then cut down on our file size. So kind of the rule of thumb here is you always want to use the roughest resolution or the largest resolution that you can in order to get your scanning done, because that will cut down on file size. You can always scan at a higher resolution if you want to, but it will potentially take more processing time and take more storage if you're saving the files. Other things to note is our scanning area, about 11 by 10 inches. Think of a kind of like a 8.5 by 11 piece of paper. That's kind of what I use to help people visualize what our scanning area is. The other one to mention is our light source. So these are 7 red laser crosses, and those laser crosses are actually 2MI safe. So they're the same classification as fluorescent lighting. You don't really need any UV protection or any laser protection goggles or anything like that when running this system, which is really nice. Additionally, the system can pick up 480,000 measurements per second. So that's really, really great for inspection applications like this, where normally you'd be probing the surface with a CMM, and the more points you probe, the longer it takes and bogs down the whole inspection process. Here, we're grabbing so many points per second that we're going to get plenty of data that we need in order to make very complex surface deviation inspections very, very easily and very, very quickly. So let's talk a little bit about the auto calibration of the cell. So what we're seeing here is, like we just saw, the MetraScan in the top of the frame on the end of the robotic arm, and kind of this T-shape or cross shape is the automatic calibration kit. So if you can see on the ends of that bar in the middle there, again, are those positioning targets that are kind of the secret sauce to this system. Those positioning targets are placed on a very stable scale bar. So this scale bar is a known value in terms of length and geometry of the ends of those targets that's hard-coded into the system. So every 5 cycles, 10 cycles, 100 cycles, you can program the scanner to come over and actually scan that scale bar, and it will compare the results that it's getting versus the true nominal results that are hard-coded into the system, and it will adjust different parameters as necessary to bring itself back into calibration if it has drifted out. So with that scale bar being mounted inside the cell, again, you can just set that to auto-calibrate every X number of cycles and make sure you don't have accuracy drift over time. That's a very nice process improvement there. So how's this whole setup controlled? So the robotic arm is programmed with a combination of this R-Series productivity station that you see on screen right now, as well as a traditional robotic teach pendant. So that's how we're going to be telling the robot what paths to take and just a general overall geometry of our part setup. Additionally, as you can imagine, if we're grabbing 480,000 points per second, there's a lot of data to be crunching around in the background in order to inspect and process these parts. So if you notice on your screen in that cabinet door that's open, we have 2 identical processing units, one on top of the other. And this goes into a function of the cell called parallel processing. So what this will do is while the robotic arm is scanning your first part, that first processing unit will start processing that mesh and begin inspection on that. And what we can then do is then switch over to that second processing unit and begin scanning and inspecting the next part. So you're never waiting on the computation time of those processing units. You'll just hot swap them in and out based on what you need automatically, and you'll keep the uptime of the arm as maximized as possible. So that parallel processing, again, for high productivity and in shop floor environments where we're really looking to crank through as many parts as possible, really helps with system uptime. Let's move on to safety features of the cell. So first, we see a nice isometric view of the cell here. We have a rolling garage door. So this door, with a push of a button, will roll up or roll down. And it's also controlled by light curtains. So if that light curtain barrier is ever broken while the door is in motion, the door will stop cold in its tracks very quickly in order to make sure that nobody gets hit by the door moving down or anything like that in case their coworker hit the close button or they accidentally hit the close button or whatever reason. It's a light curtain controlled garage door. If somehow someone is inside the cell setting up while somebody tries to close the garage door or start the inspection program, there are several floor radars around the perimeter of the cell that will prevent that from happening. So if that floor radar is broken by an employee standing in the cell, or maybe some parts that aren't supposed to be in the cell are there and potentially cause a crash with the robotic arm or the turntable, that floor radar safety net is going to prevent that from happening. So we have door safety and floor radar safety on this system. So we kind of did a general overview. Let's take a look at a specific example here so you guys can kind of get an idea of cycle times and setup times for parts of this kind of complexity. So we have a transmission case here, and we're inspecting this transmission case. So we can expect something along this complexity to take around an hour to an hour and a half to program. And that's going to involve all the different motion of the robotic arm, motion of the turntable, different inspection points, different tolerances of the inspection points on this particular part. 5 to 10 minutes for fixturing setup. And so kind of use the term fixturing loosely here. It's not really hard and fast fixturing like you're used to. It's more of a loose, flexible fixturing. You can see we really only have 3 clamps here. We're just trying to hold the part loosely in the same volume from part to part. Obviously, we don't want to be anything like 6 inches off in our setup here, but if we're within a plus or minus an inch or so, as long as we aren't going to hit the robotic head as it goes through its scanning procedure, the mesh will actually self-align to the CAD model once we're done processing it. And so it being a little bit off part to part is nothing that the system can't filter out very, very easily. So a very quick and easy fixturing setup is nice. And then once we have our program and we have our fixturing set up, all we have to do is pop the part in, clamp it down, and then set off the program, and that takes about 2 minutes for this particular part. So we can see setup is actually the majority of the time here, and once you get that set up, every part after that will be relatively quick. So you can see with this kind of a setup, we get about 660 parts per day. So it's a very quick inspection process. It's versus a CMM, I call a CMM kind of like a serial process. You have to do one point after the other, after the other, after the other, all in a row. Whereas a system like this is a more parallel inspection process. Once we have that mesh of that part, so it took us 2 minutes to scan the mesh for this, we can inspect pretty much anything on the surface of the part almost instantly. Like I said, it takes a little bit of processing time in the background, but nothing that's going to take more than the actual scan of the part itself. So you basically, whether you have 10 inspection points, 100 inspection points, 1,000 inspection points, your inspection time is going to be very, very consistent, and it's not going to grow linearly with number of inspection points like you would see with a CMM probing system. The system also has a bunch of real-time productivity indicators, as we can see here. So you've got your running uptime on the system, your scan count, and then your average scans per hour or average scan time, kind of the same thing, but good to see broken out in 2 different ways. So as we can see here, about 2 minutes, 121 seconds per scan we've averaged. So that's gonna be the conclusion of our Cube R overview.
Yeah, I don't see any questions come through. Let's see. Oh, one just popped up. Does this provide a file I can export to, for example, SolidWorks?
Yes. So what the scanner is actually generating, what you're seeing on the top right of our screen right now, is what's called a mesh file or an STL file. It's built up of a bunch of very small triangles on the surface of the part. So this particular workflow that we've covered today is for inspection purposes. So we take that mesh and we compare it to an already existing CAD file. We use that CAD file as our nominal. The manufacturer Creaform has another type of software for exactly that application, for reverse engineering applications where we have a part that for whatever reason we don't have a CAD file. Maybe it's a very old part, maybe the data was lost, but we have the part physically sitting in front of us and we want to make a nice CAD file of it, a nice parametric SolidWorks file. That software is called VX Model, and yes, that's exactly what it's made for. It's made for taking this organic mesh that doesn't really play that nicely with SolidWorks and turning it into, with a little bit of work from the designer, into a parametric CAD file.
Well, I think that was the one and only question. Got a nice thank you. So with that said, I'd like to thank everyone for joining us today. Thank you very much, Colin, for putting the presentation together and going through it. And wish everyone a good rest of their afternoon.
All right. Thanks, everyone.